So just to review the concepts first of two-dimensional locations and so on. So we have our standard x and y axis, and we have a point here called P. P is in a specific location. It's not here, it's not there, it's not over somewhere else, it's right here. And so however we describe point P must be specific. So it is inadequate to describe it simply as a distance from the origin, because a point here would be the same distance, or a point there would be the same distance. So not only is it the distance we're talking about, it's also the direction. And that's what makes the concept of the two different variables. This is a vector, where if we don't give the direction, the description is inadequate, is incomplete, and arguably meaningless. Furthermore, I want to remind you that we can describe the location of point P here in two ways. We can describe it as an angle from the plus x-axis measured counterclockwise to the point of the vector in degrees, and we'll designate that with the letter theta, the Greek letter theta. And of course we can have a distance. So we would say, in this what we call polar coordinates, this is our units from the origin to the point at an angle of theta degrees. Now this might sound strange to you based on your math class, but actually this is how we identify things in the real world. If we say to you, we were to say, where's Montreal located? You would say, well, 500 kilometers east-northeast of Toronto, for example. And that is a exact same concept here. Of course, the other way that we can describe the location of P is through what we've learned in our math class, and that is so many x units this way, so many y units this way. And that describes P as well. Because if x is different, that will move P. If x is negative, it'll be over here. If y is negative, it'll be down here or something else. So either way, the r theta description, what we call polar, or the xy description, which we call Cartesian or rectangular, both specifically describe the location of P. And a vector that locates something is known as a position vector. Now, the important thing for this work is what any vector we describe, whether it's position, velocity, acceleration, what have you, forces and so on, we're always going to use the same construction. We're going to, if we're looking at polar angles, we're going to measure them from the plus x around counterclockwise. Not just to 90, but all the way around. And this is something that many young people have trouble with. It seems that when we get past 90 degrees, we get scared. Somehow we want to use another angle. And we'll show that to you in the next plate. But, as I said in class already, the problem is that doing calculations using polar coordinates is practically impossible. Whereas doing them with x and y vectors is very easy. But since people are so much more used to our thetas in our understanding of many things, for example navigation, as I said earlier, we often enter vectors as polar in polar form, convert them inside our devices to rectangular form, do the calculation, and then convert them back to polar form again for display purposes. Now this all seems very convoluted, but we have to recognize the phenomenal computational power of the modern processor. So once again, we have a point P here. It's located from the origin, and this set of axes and the specific origin is what we call a frame of reference. And we have to, if we're going to have multiple points, so there's going to be any motion here, everything must be referred to this point and the set of axes. Otherwise, we're talking about different things. And so again, we would refer to it in polar form, r theta, or in xy form, in rectangular form. So once again, we have our xy axes. This is the plus x, the plus y, This is the negative x and the negative y. And now we have our point P. I've added 3 more, point B, C, and D. And just to look at how we measure these angles. We're measuring the angles counterclockwise from the plus x always. No matter what angle is given in the problem, no matter where it's drawn, we always measure the polar angles from the plus x around to the vector in the counterclockwise direction. And you may have to do some transformations and calculations to find that angle, but that's what you're going to do. So we first had theta here, and we'll say theta sub p. So now we're going to have an angle that goes all the way around here, which we would call theta sub b. We're going to have an angle here that goes all the way around to this one, so theta sub c, and the big one all the way around here to d. And we'll call that theta sub d. Get used to subscripts. We use them all the time. Once again, we want to keep subscripts to 1 letter or 2, but it should not be much more than that. Now let's imagine we have a question where they might give you angles like, say, 20 degrees right here, 10 degrees here, 25 degrees here. Let's just suppose you get questions, and that's the information that you're given. You're not given the big angle. But we know some things from our elementary geometry. We know that from here to here is 90, from here to here is 90 to 180, to 270, and finally to 360 again. All of our angles must be quoted between 0 and 359.99 degrees. So we can use some of our basic logic here and say, well, okay, if this is from here around to 180, then this is 20 degrees less, and so this one is going to be 160 degrees. And that's the angle we want, is that number, okay? This one, if we go all the way around here to 270, then we subtract 25 and we get 255 degrees. And finally, this one is 10 degrees more than 270, we'll make it 280 degrees. And so I'm sharing this short segment with you just to convey to you the importance of using the angles measured from the plus x, even when the given angles are different and coming from different axes. Now here's the simple reason why. If we measure this vector using this theta p here, and it's say 50 degrees or something like that from this angle to here, and then you measure this one relative to this one, and this one relative to that one, and that one relative to this one, those angles are not measured from the same reference. And so when you try to compare these vectors, you get garbage. We must measure them from the same agreed location every time. Now the reason that we do this is to facilitate the taking of xy components, the xy values, which will allow us to make calculations very, very easily, which is the next step to this review of 2D vectors. So once again, from the plus x, we measure counterclockwise around no more than once, okay? And we make sure that our angles are always measured all the way around. We don't accept these smaller values, okay? And that comes with remembering it's not very difficult. You just have to pay attention to the standard. If we do it this way every time, whether it's position, velocity, acceleration, forces, whatever, we do it the same way every time, then our methodology becomes standardized. And we don't waste time reinventing the wheel on the method that we're going to be using. And that makes, that way we can spend time on the other more important complexities of any given problem. So when we want to convert often polar vectors, typically for navigation or other types of situations, we have to convert them to x and y, to ordered pairs, so we can do calculations. This is easily done from the triangle. based on Pythagorean theorem and some elementary trigonometry. So if you recall, if we look at the x value first here, if you have the angle theta here, its cosine is the adjacent side divided by the hypotenuse. And you see that here. Similarly, the sine of theta is going to be the length of the y side divided by the hypotenuse. We then rearrange these equations very simply, and we get x equals r cos and y equals r sine. And so, once again, if this is valid, if we measure the angle from the plus x around, then these relations are always true. And it doesn't matter if it's position, velocities, forces, or whatever, we could still use exactly the same relationship. And this makes life easier for us whether we're writing code or we're doing calculations with a pencil. And so this is what we call, in the parlance, taking components. And we will do this very, very often, especially in multi-2 and beyond dimensional type calculations. If you write code, computer code, to solve motion problems, you'll be doing this as well. Now, many of our 2D questions that we're going to be asked to solve are related to navigation, understandably. And so we have to look at this because the way angles are given in navigational purposes are different than the ones we need for our calculations. And this requires us yet another conversion. If we look at the standard compass, you see you have north and south, west and east. Now these correspond to the plus x, plus y, minus x, and minus y axes. However, compass angles are not measured the way that we measure plus or our theta angles. Compass angles are measured clockwise from the north, or from the plus y, if you will. And so they are different. And that is the tradition of measuring compass bearings, as we call them, as they like to say, east of north. Okay? Yet, we've been already taught that we have to measure from the plus x. And we cannot change that just because we're doing navigation. We don't get to do that. So we have to convert. Now first off, in this particular situation, if this angle for P here is 30 degrees, then the angle from the north down to P is going to be 60. So we can see here that the gamma, if you will, the symbol I'm using for compass bearings, would be 60. We take the vector here A, the angle comes all the way around now, and we're 40 degrees short of 180, because we started here, come all the way around, that'd be 180, we're 40 short, this is 140 degrees. And for B, we've gone all the way around, 270 plus 20 is going to be a compass bearing of 290 degrees. Now, the point is that we cannot, and I emphasize the word cannot, we cannot use these navigational angles. Instead, we must use the XY angles. And so we have to convert these gammas, these compass bearings, into these XY angles. Now thankfully, the calculation is fairly easy. Here is the equation here, and just to elementary algebra will tell you, you can simply switch it like this. So it is a very simple arithmetic calculation. So if we were to do it in this example, we already know that P is 30, it's given to us. If we come around here on the long, sorry, I misspoke, this 140 here, now we can sometimes infer from the diagram, but sometimes we don't get a diagram. So if we just take the straight math, we say 450 minus 140, okay, gives us 310. And that seems reasonable because we would come all the way around 270 plus 40, and that would equal 310 degrees. And that's the angle we need. If we look at, that's A, we have P, so over here to B. In the case of B, we're at 290. If we subtract 290 from 450, we get 160. But if we go this way around, you'll see that we're 20 degrees short of 180, which is in fact exactly 160 degrees. And so the challenge we face is that we have to convert from the navigational angles to these XY angles. None of this is difficult. You just simply have to pay attention and practice. Here's 3 examples of it. It's all very straightforward. Now there's one more issue with navigation. Well, there's actually 2 I'm going to show in the next pane here before we can get into some calculations. So we have 2 things to think about here. First is the wind. When you listen to the radio or whatever and you get the weather, it will tell you that the wind is blowing from some direction, say the northwest, at such and such a speed. And that's perfectly reasonable, and we often do that because if a town where the area is right now is experiencing, warm weather or something, then that weather is coming to us. And so the weather that's coming to us is what's interesting to us. So it's perfectly reasonable for the weather people to tell us where the wind is coming from. But regardless of that, when we do our computations, we have to remember that we still have to make sure that our vectors, that our way of describing these parameters is valid on the frame of reference we're using. In the case of this, you'll notice that the vector is pointing towards the origin when in fact it has to be pointing away from it. That's the way we set it up. So in fact, the wind may well be blowing from the northwest. Okay? But what we care about is which way it's blowing to. And in this example, it will be the opposite. It's blowing to the southeast. And so the bearing is plus or minus 180 degrees. So again, none of this is difficult calculations. You just have to be aware of what's going on. So if you get a wind direction, you're going to first convert it by 180 degrees. Then you're going to convert the bearing, that 100, whatever it is. In this example, it would be 135. Okay, you originally got something over here at 315. But then we convert it to 135 by moving it, so it's pointing to the direction it's going. And then you have to convert it to theta, as I showed in the last pane. So there's just an extra step here for the wind. Now this is not something to criticize so much, it's something just the way we do things that makes it important for all of us to understand. The second part of this is a terminology that's used in angles, in navigational angles, that I personally think should be discouraged, but nevertheless it shows up in the textbooks, and so we have to cover it because it ends up on evaluations. It's what is known as a relative bearing. Unfortunately, it's not even done very often correctly in the books itself. We have our primary compass directions, north, east, south, and west. And if we take an angle here, a compass bearing of 310 degrees, the first thing we're going to do is decide which of these is closest to 310 degrees. If we know we go all the way around to west, and that's 270 plus 40, okay, so west is closest. So we would say west, in a big capital letter here, just to emphasize it. And then we have the correction. It due west, and then there's an angle. And we'll take this, not so much this diagram, but this number here. So this is 40 degrees, and it's which way? Is it south of west? No, it's north of west. So we're going to say 40 degrees north. Now the W is large in my example here because it is the primary direction. So this value here should never be not greater than 45. The correction should always be less important than the compass, the primary direction. Fortunately, that's not done very well. So I wish this whole thing would disappear out of the books. I've only seen it in textbooks and in geology books. There's no way you'll ever see this type of notation used in commercial navigation. It is too easy to make a mistake. And whether we're flying an aircraft or a supertanker on the ocean, we have to make sure that our directions are bang on. You know, sometimes bad things happen, but we don't want them happening for stupid reasons. And so this is the type of complexity, you know, you could easily mix up these directions. It'd be very easy to confuse it. It also makes you have 3 pieces of information here that you have to send and communicate, where here you only have 1. And so, you know, for professional reasons, there's no comparison. But anyhow, you may get navigational directions given in this description here, or in this one. You need to be able to convert back and forth. Okay, and that's the logic behind the relative bearing. So that's a little bit of a review. I want to go back over now some basic arithmetic of 2D vectors and get people used to that type of calculation before we actually get into solving navigational questions. So when it comes to vector mathematics, we have to go carefully. What we found initially is that vectors can be added and subtracted just like real numbers. Obviously, when we get into ordered pairs and so on, it's a little trickier, but not too bad. The main point, the overriding point with any kind of operations in 2D is that the x's are taken as a separate entity and the y's are taken as a separate entity. You get into trouble when you combine the two. Okay? If you've got something going to the left and something going forward, and you simply add those 2 values, it shows you don't understand what we're doing. So here's algebraically the x and y coordinate of vector A and vector B. This symbol, of course, is simply the symbol to imply that we have a vector. It's not a single variable. And we're choosing to add these 2 variables together, these 2 vectors, and obtain a result C, which we call the resultant. So instead of it being a sum, as you typically do when you're doing arithmetic, when it comes to vectors, the sum of 2 or more vectors is known as resultant. The calculations using rectangular coordinates are very simple. We simply add the x coordinates, we simply add the y coordinates, and we're finished. There's nothing else to it. It's incredibly quick. An example, numerical example to the right here. If we had vector A, a position vector, locating an object at -5, +7 meters, and another one, vector B, locating some other object or some other position at +3, +8 meters, and we combine the 2, we end up at the end with a -2, +15 meters. Notice that the plus signs are there to imply direction. To make sure that, especially young people, when we're first getting started, I ask for explicit direction signs. So whether the object is to the left or the right of the origin, you must put in the plus sign or the negative sign specifically when we're doing this. And again, it is really that simple. And of course, the important thing about this is that we can add any number of vectors. So if we had a D, an E, and an F, you'd simply add all the X's and all the Y's, okay, as appropriate. And this would help you going along. And you can write code to do that as well if necessary. So this is why, for example, I don't allow cosine law, because you can well solve a situation with 2 vectors. But as soon as you have more than 2, you're in big trouble. And we don't want to learn methods that are clumsy like that. They're not going to help us in the long term. So as I said before, cosine law and sine law, those types of methods in my course are banned. If you use them, you get no marks, as if you didn't do the question. The last type of operation that we'll need to consider for this section is what we call scalar multiples. And this is when we take a vector such as A here, which has 2 coordinates to it, and multiply it by a real number, which is what we signify with this line. It just simply says that the variable B is an element of the set of the reals. And so if we take any real number and multiply it by the vector A, what we do is we multiply B by each of the coordinates. So you can see B times AX and B times AY. It's really a simple calculation. What this does is it makes the vector longer or shorter. In other words, this will increase its magnitude or reduce it. Over here, you can see a numerical example. If A starts off at -5 + 3, and B is 4, we end up with -20 + 12. Pretty straightforward. However, there is a special case. If B is negative, you follow through the same way, but the result is, in addition to changing in this case, doubling the length of the vector, it also reverses the direction. So if the sign is negative, this reverses the direction of the vector. Otherwise, scalar multiples do not change direction. Of the vector, except if we have a negative scalar multiple, then you get a reverse. Okay? Now that is the basic review of 2D vector and 2D vector operations that matter up to now. And I think I'll stop this video with these ideas, and then we'll get into the types of questions that we can consider.